We're now recording. Right, so if you're watching this, you joined us a bit late because I forgot to turn on the recording. We were going over these facts about T. The most important things are that T and Z are almost the same. And that for T, you have to look at a special table which lists the probabilities in terms of the degrees of freedom, which is one less than the sample size. Here we go, and we're down here, right now we're on number 7. S over root n is called the standard error of the mean, since it is the estimated standard deviation, I guess, of x bar. I should put that there like that. So standard error of the sample mean, really thinking. We usually call it SEM, standard error of the mean. Go SEM is S over root n. You might see that printed someplace. All we need in order to use T are simple random sampling. And like we had to do for proportions, we want the sample size to be much smaller than the population. Of course, the population's normal is probably pretty big. If it's a small population, it won't have actually a normal distribution, because the normal distribution can take on millions of values. So probably that's not a big deal, but sometimes it is. A normal population or a large sample size, so that the central limit theorem says X bar has a normal distribution. So ordinarily we're looking for simple random sampling, normal population. Okay. Let's see. Proceeding on. An example of T. Example of T in action. 20 young adults were presented with recordings of 100 pairs of speakers of the same gender, each speaking the same phrase. Each young adult then attempted to determine which of each pair was taller just by the sound of their voices. So 2 people talked. They said, I think the first one is taller, or I think the second one is taller. The number of correct responses out of 100 for each of the 20 is listed below. So they tried 100 times, they were right 65 times. 59 times, and so on, 70 times. Some people are really good at that, I guess. I don't know how you do it, but we know a lot from people's voices. I know when I hear a singer and I don't recognize their face because they're so old now, I still recognize their voice. There's something about voices that stamps on our brain. So it's clearly they mostly did better than just guessing. They all beat 50% except one person here got 49. Not very good at listening to how tall a person is. Let's check this with a hypothesis test. So the 2 things we check are simple random sampling and normal probability distribution. Let's assume the young adults were chosen as a random sample of young adults. And then we're wondering whether these kinds of values have a normal distribution. So we can make a normal probability plot. I'm going to do it because that's some of the things we do. Okay, so we want to do that. We need to enter this data. So I'm going to do that. 65, 61. I'm looking at 3 things at once. It's hard to do. So I'll check them okay so far. 65, 61, 67, 59, 58, 62, 56, 67. That looks all right. Okay, so the 67, 61, 67. Okay, and then on the next row, 68, 49, 66, 58, 69, 70, 65, 56, 68, 56. There's 20, so 20 is a pretty big number, but not quite the 30 or 40 that we'd like to see to be safe. So we're gonna check normality right here. So we go to stat plot, which is here. Well, it's second here, second stat plot. How about that? There we go. And then we're in plot 1. We hit enter to go in there. Make sure it's on. Okay, that's on. And then I'm going to come over here. The last one is the normal probability plot. I hit enter for that. And we've got our data in list 1. So I can leave that alone. And this one, we don't really care, data axis, X or Y. Just which values are the 60 to 70, which axis is that on, and which ones are the sort of predicted positions. We'll just put that on X and that on Y. And then, of course, it doesn't do anything because you haven't asked it to graph. So that's all set up to go. We go over to graph not knowing what's going to happen. I don't know what that is. Probably we've got the scale set to for some other reason. So I'll go to zoom and then make it fit. So there those values are in a normal probability plot. What we're looking for is no clear curvature. It's close to a straight line. That's pretty much how things go. This side, it looks great. This side's a tiny bit curved. But overall, pretty straight. So no major curvature. And so we'd say it's approximately normal. Plus I've got 20 values. Those two things together probably make us happy enough. So we don't want to see outliers. Outliers would show up in a curvature of the graph, or skewness would show up as curvature of that normal probability plot. It's pretty straight. So we did that. Okay, off we go. So then we're going to test the long-term mean mu. And what we want to know is, long-term, do you think they're doing better than guessing? So is it possible the mean is just around 50%? Or does the data seem to indicate the mean is bigger than 50? So there were 100 tries, 100 pairs with speakers. So beating 50 is more than half right. It says, before we proceed, let's see how big T has to be for the result to be considered statistically significant. Oh, let's do that. So here's my T tables. The sample size was what? It says 20 pairs, so 20. So here, 19 degrees of freedom like that. And then we're wondering, is this a one-tailed or two-tailed test? I'm wondering. Trying to get so I can see everyone. Not having much success. Where is this? Here we go. Let's spread this out. Here we go. That's better. So I'm talking to Gage, I guess. What do you think we have? A one-tailed or a two-tailed test?
One-tailed.
I have a hard time hearing you. I'll turn this up. Go ahead.
Is it one-tailed?
It's one-tailed because it's this greater than. Two-tailed would be not equal to sitting there.
Okay.
So we're going to reject if we see a T in the upper tail, far enough up in the upper tail. We'll measure that by using a p-value. So it's a one-sided test. And then we want statistically significant. So we want that tail to be less than or equal to 0.05. So I'm here in the tables for a one-tail test, talking to Donnie. We're thinking this is the tail we need to use, the 0.05. Here's the degrees of freedom. We have to use 19. So what do you think the critical value is? I'm moving this around, sorry.
It would be 1.729.
This one here, 1.729. So that would be this position here, 1.729, to have 0.05 probability in the upper tail. If you beat 1.729, the upper tail will be smaller than 0.05 in probability. And we need 0.05 or less for the results to be considered statistically significant. So we're looking for those kinds of values. So we need T to be at least, what do we say it was? 1.729, like that. I have the feeling we're going to do a lot better than that because it's obvious, right? When you see something like this, you go, I don't have to do a test. It's clear they did better than guessing. We should get a T way out in the tail. When you get something close to the 0.05, you go, well, it might be maybe something happened. I'm not sure. It looks like it might. This is, I'm sure, already without doing any testing. So we're going to get a big value for t. That's what I'm thinking. Haven't done it yet, though, so about to find out. So now we're to compute t. I need to know things. We haven't been given anything. So I need x bar and s. So luckily, I've already entered it in my calculator. So I'm going to go to stat calc, one variable, and I'm going to hit list one. Yeah, calculate. So there's the stuff I need. So I want to put that here. I'm over to Crystal. Can you help me fill in the quantities here off my calculator?
Your X bar would be 62.4 minus 50. And then your S would be 5 point, is it the 669?
It is.
Okay.
So that's the one with S on it, right?
Yes.
It doesn't look identical, but it's that one. That's the one you need. This is the one.
Yeah, because that's a standard deviation one, right? For the
It
S.
is. It is. This sigma, in the sigma in the formula, you divide by n instead of n minus 1. And that's not the one you use with data. So put that here. And then square root of 20.
Divided by square root of 20.
Okay, so I'm going to type that. Second quit. So parentheses 62.4 minus 50 divided by parentheses. I need parentheses here. 5.6698 divided by the square root 20, get over, close it up. So if you don't put those parentheses, I think it just takes the number, divides by 5, then divides that by square root of 20. That doesn't work. You got to make sure you're dividing by that whole denominator. So we have to put parentheses around the denominator. So this is supposed to be a number like 4, I'm hoping. It's 9. Nice. 9.78. Yeah, I was thinking it wouldn't be on the table. So that's what happens here. When you know without knowing anything, something happened, when you compute a test statistic, it's going to be off the charts. So we go to the tables, and we're looking for 9.7, and we're in this row here, 19, and it just doesn't happen. We'd have to keep going a long ways. These p-values get smaller and smaller as we go, right? So we'll just claim the p-value is less than 3 zeros and a 5. The p-value is less than 0.0005 from tables, because they don't go past that number. So that's the last number we see up here, 3 zeros and a 5. So we would say, here's the p-value calculation. We draw a picture of t. Go out here to 9.78. We want to shade this side. Oh, so I can't. Maybe I'll ask the calculator to do it and see what it really is. Let's see if we can do that. So we'll go back to stat, tests, t-test. We have data. We're using 50 for the null hypothesis mean. We're in list 1. We're wondering if it's greater than 50. And then we're going to go down to calculate. Now it'll do it when I hit calculate. So it gives us the 9.7 that we had for t. It gives a p-value 3 times 10 to the minus 9. So 3.75 times 10 to the minus 9, like that. So that's like this. 1, 2, 3, 4, 5, 6, 7, 8, 3, 7, 5. Pretty tiny.
Where'd you find that on the calculator?
So it's right there, p.
Okay, but how'd you get to the t-test?
Oh, how to get to the t-test? Okay, go back. We go stat, test. Go to t-test. And then when you go into t-test, hit enter. It gives you the option of using already computed statistics, which you might be given, or data, which you might have entered. And we already had the data, so I used that. It even has this draw feature, which is kind of silly because you would never actually draw it unless you had to turn it in for homework. I mean, you draw it for fun. And now I can't, oh, there it goes. So there's what T looks like. Of course, it's going to try to show you 9, but it can't. So it doesn't look like it did anything because 9 isn't even on the picture here. It's way over here someplace. I could try zooming it, but I don't think it's going to help. Oh, now I'm probably, yeah, so I just get back to that thing. So it doesn't help. Okay. There we go. It says state conclusion. Well, we're going to reject HO. That's the first thing we have to say. So we have to say that's the first thing. So the first thing is accept, oh, sorry, fail to reject or reject HO. So that's, we have to figure that out. So we say we're going to reject HO. And then ordinarily you would say something about the results. The results are considered statistically significant. Since the p-value is less than 0.05, for sure enough. The very small p-value makes us very sure. Sure, I was going to spell with an H. Sure, HO is not true. So it's beyond statistical significance. It's the tiny p-value. It's almost impossible that the null hypothesis could be true. And so we could then say for 4 something about what does it mean? Students do better than guessing long term. We're pretty sure that's not just luck. Students do better than guessing long term. It'll happen if we keep running this experiment for a long time. So accept or reject, talk about statistical significance. Someone probably wants to hear that. Because when someone's looking at experimental evidence, they want to know, is that random variation or not? So it's not. And you want to talk about the strength of the evidence. Very tiny p-values is very strong evidence. And then you want to state what's happening in the context of it. To answer the question, do students tend to do better than guessing when deciding who's taller based on voice? They do better than guessing. Long term, it looks like they will keep doing that. That's not just a random thing. It just seems to be a fact. They do slightly better. Well, slightly better, I don't know. So if you wanted to know how much better, I guess you can make a confidence interval to see where you think the long-term mean is. Maybe they'll ask us to do that. I can't remember if this is on here or not. Here we go. Looks like it is. If we reject the null hypothesis, we usually compute a confidence interval to determine where the long-term mean actually is. If the case is clear-cut, we can use a high level of confidence, say 99%. So we'll be really sure the true mean is in there. Okay, that's a clear-cut case, so it shouldn't be too hard to do that. We shouldn't have too wide an interval, we're thinking, but let's just see. So n is 20. We're looking for 99% confidence. I now need some help from Kat. I need the critical value for 99%. Can you help me?
Yeah, is it Sorry, I'm doing my phone. It's just really small.
So I need to know which number to pick here for 99% confidence. You know which one to choose?
Yeah, wouldn't it be 0.01
Well,
or sorry, 0.001?
here's the problem. The picture looks like this. Here's the bell curve. It's not the usual bell curve. It's for t. We want 99% here. We want to figure out what that number is, t.
Oh, then you would take the 0.00 or the 0.01 on the right side of the curve.
Hang on, that's 99, right? So there's 0.01 left. You got to split it into
Yeah.
two pieces. One half is here, one half is here.
Yeah, so you would just take like both each side, one to the right and one to the left.
So what does that mean in terms of the right tail? Which tail probability am I using?
0.005
Okay, there we go.
because it needs to add to 0.01.
That's half of 0.01, right?
Yeah.
Okay, and then we're going to come down here to the degrees of freedom 19. I'm doing that here. So it looks like it's 2.861. Let's put that in there. Double check that. It looks all right. 2.861. Do it. Okay. T is 2.861. We said that. And we could write it. We could write it T.025 is 2.861 if we wanted to. Sometimes the people write T star for critical value. Either way. And then the confidence interval is x bar plus or minus that critical value s over root n. We have s somewhere. We just had it. Let's see what it looks like. So we've got all the stuff we need on the previous page, do we? Yeah, so x bar was 62.4 plus or minus t star is 2.861. S was 5.6698 over the square root of 20, like that. And you know what I'm going to do right now? I'm going to stop recording because if I record too much, things get bad. So I'm going to go back here